Hi, my name is Judit and I'm a PhD student at Penn State University working with Dr. Krista Wotier. For my PhD, I've been studying flank instability processes at volcanoes through remote sensing. Today, I want to highlight the potential of InSAR time series analysis for detecting small magnitude long-term displacements, particularly at remote or poorly ground instrumented volcanoes. To do so, I will be presenting the case study of Pacaya, pictured here, an active basaltic stratovolcano in Guatemala that shows evidence for past collapse. The study of volcanic flank instability is important because flank collapses have caused many casualties in the past, but some challenges in identifying flank instability at volcanoes include a lack of instrumentation, flank displacement magnitudes that might lie below the detection threshold of the available instruments, and larger magnitude signals that might obscure the slip signal that we're interested in. Pacaya volcano has experienced past collapse, which left a collapse scarp, shown by the black line on this map. In addition, factors facilitating a future collapse have been identified. As we can see on the southwest-northeast profile on the bottom panel in this figure, Pacaya sits on a south-sloping substrate, is buttressed on the northeast side by the Cerro Grande and Cerro Chiquito domes, and might lie over a weak layer of pyroclastic materials, shown in yellow. Moreover, flank motion was identified through differential InSAR during large eruptions in 2010 and 2014, which produced the lava flows shown in green and in brown. My aim was to investigate the potential to detect long-term trends of surface displacements between these two eruptions and use these data to model observed displacements and their interactions. We can partly overcome the challenge of lack of ground instrumentation by resorting to remote sensing techniques such as InSAR, where the difference in phase between two radar images given a deformation event is used to provide the centimeter scale deformation in the line of sight of the satellite. Conventionally, we look at the displacements between two consecutive dates, as was done to identify the 2010 and 2014 displacement events. However, coherence can be lost for time intervals greater than a few months. In this study, I applied an InSAR time series technique that is capable of extracting smaller magnitude signals spanning longer time intervals by performing a least squares inversion of the radar face for each date relative to the first date using a greater number of interferogram combinations. We used two synthetic aperture radar datasets from the Cosmos SkyMed and RadarSat 2 satellites, beginning after the 2010 event where we saw co-eruptive flank slip, spanning this volcanically quiescent period, and also the 2014 co-eruptive period where we expect to see flank motion. We performed InSAR time series analysis on each of these datasets individually. Here I show the time series results. The plot on the right shows the line of sight displacement of the pixels represented by the red square on the Google Earth image over time. The blue circle on the map shows the time series reference region, and the vertical dashed lines show the times of high and vigorous volcanic activity. We found that the southwest flank of Pacaya was moving away from the satellite at about 2 centimeters per year from 2011 to 2013, and this increased to 18 centimeters per year in 2014, coincident with more vigorous volcanic activity. Having identified these two displacement rate trends, we wanted to see what the best fitting sources could be for each period, the pre-2014 period shown in orange and the co-2014 period shown in blue. We performed analytical modeling jointly for both datasets, but individually for each period. The top panels on these side plots show the observed displacements for the pre-2014 and the co-2014. The middle panel shows the model displacement, and the bottom panels show the residual displacements. We found that the pre-2014 displacements are best fit by a southwest dipping detachment fault, and that the co-2014 displacements were best fit by the same fault and the addition of a dike intrusion, with strike and location close to the eruptive 2014 events. Finally, through static stress changes modeling, we found that dike intrusion could have facilitated slip on the model detachment fault, explaining the faster slip rate during the 2014 eruption, and that fault slip itself can also facilitate further dike intrusion. In conclusion, through InSAR time series analysis, we were able to reveal southwest flank creep at Pacaya that is accelerated during magmatic intrusion. This highlights the critical value of InSAR time series analysis for revealing small magnitude flank slip at volcanoes that might otherwise be overlooked. Looking forward, thanks to a 6-day repeat pass for Sentinel-1 and the availability of ascending and descending orbits, we now have much denser coverage, which will also allow decomposition into horizontal and vertical motion components to better constrain any ongoing flank motion. This could also help identify slow ongoing slip at other poorly instrumented volcanoes. Thank you very much for your attention. If you want more information, feel free to follow this link to the full JVGR paper.